Let's do some online only CSE 116. Hell yeah. Okay, so we are. Oh, and I'm going to hit my peak viewers. Hell yeah, I am. Uh, the most viewers we've had. We're going to definitely be the top of programming, basic programming. Okay, so let's get on track. Get back on track and get back into the course. I will have the lecture portion from 1 to 150. I'll try my best to keep lecture in that time frame. So it'll be 1 to 150 as a typical lecture. And then I'll cut the stream just for a brief moment, just so Twitch will mark that as a separate video. And we can upload that video to YouTube. And people can watch that lecture while I'm still streaming. But then I'll stay on for at least 1 hour. I'll stay on at least till 3 each day, answering questions, interacting with chat. And that's where we can talk about all the questions. That's where I'll just be interacting with chat. During lecture, I might miss your questions. I'll be trying to blow through the material and get through it. As you all know, this course, there's a lot of content to cover in each 50-minute lecture. So I'll try to get that content, and then with the Q&A, we can go over examples, you can ask homework questions and all that stuff. So let's get to it. Let's get 116 back on track. So looking at the high level of the course, we have these 3 learning objectives that we've completed. Program execution, which was a little bit of how a program executes while it's in the machine, talking about memory management. And I use this, at least in part, as an intro to Scala. What is Scala? What is this new language? What is all this new syntax? But then I put that under the guise of memory, because we do talk about that quite a bit. But that doesn't take up the entire learning objective. So program execution, how does a program run on a computer? Then we had these 2 kind of dual, kind of competing paradigms, object-oriented programming and functional programming, where when we're designing a program and when we're writing our code, really designing at the program level, how do we structure and how do we think about our programs? Object-oriented programming was all about state. We have objects. Objects carry around state and behavior, and the state affected the behavior. When we moved to functional programming, we took away the state. Functional programming says let's only think about pure functions, input-output behavior with no state. And also using first-order functions, where we can pass functions into in as arguments. We can store functions in variables. We can return functions. We can do something called function currying, which we use, but I didn't really talk about by name. I didn't really call it by name too much. But a lot of different things that we can do with functional programming. So when we design a program, we kind of think, do we want to take an object-oriented approach? Do we want to take a functional programming approach? Do we want to mix these paradigms and use functional and object-oriented, which we'll be doing in the course moving forward? Or do we want to use neither of these paradigms and just kind of hack away in a big old main method? These are 2 tools in your toolbox now that you can use to approach your programs. And for each one of these sections of the course, I forced you to use that specific paradigm that we were talking about. Whatever one we were talking about, I was forced. Oh, my cursor's on the wrong screen. I was pointing, but you couldn't see it. Whatever paradigm we were teaching what I was teaching at the time, I would force you to use that paradigm. I took away conditionals and control flow and object oriented. I took away mutability in functional programming, as you all know, as you're all well aware. Moving forward in the course, and as we move on to data structures, I'm going to take away those restrictions. We're done with the restrictions. I've showed you those 2 ways to approach designing a program. Now it's up to you, or up to however a specific assignment is structured, to be able to decide which paradigm you want to go with. Do you want to mix them, or do you want to use neither of them? What combination of these things do you want to use? So no more restrictions for the rest of the semester. And we're going to start talking about data structures and their algorithms. So with data structures, I shouldn't say no more restrictions. No more restrictions on what you do, but I still might give you a class that is immutable that you have to work with. I should clarify that before someone calls me out on it. So with data structures, we're going to talk about 3 specific data structures: linked lists, trees, and graphs, and algorithms that we can use to be able to work with them. How do we represent our data in these data structures and work with these data structures? Write programs using these data structures. How do we expand these data structures? And how do we just generally get things done with these structures, and how do they work under the hood? So that's what we want to move into now. And then, of course, it's on the screen, so I'll mention it. Event-based architectures will be that last learning objective of the course. So where am I? So I won't really, chat's going a little fast. I won't be able to keep up with chat during lecture if it's going like this, but during the Q&A, I'll interact with the chat much more. And yeah, questions about your learning objective, your specific stuff, I'm not going to answer those during the lecture or Q&A. Make a private post on Piazza or go to office hours, and we can chat about that stuff. But yeah, my first learning objective is not upgraded. I mean, I guess this one I can't answer. I haven't looked at the first learning objective again yet. I haven't revisited that. After I did the OOP grading, I didn't revisit that one yet. I'll get to it. It'll happen. I want to finish up homework 2 grading first. Once I get that out, I'll shift gears into revisiting learning objective 1 and also getting the next round of homework. So my to-do list is always seemingly infinite, so I'll get to things. I was hoping to get caught up on everything over the break, but we go to online only. I had a lot of adjusting to do. So I kind of lost a lot of time there, as we all did. So let's get into this. Let's do the lecture content, and then we can Q&A after. Linked lists. We've used linked lists throughout the semester. We used the linked class in Scala, which is a linked list. But let's talk about how that works and how we're gonna how a linked list is actually implemented and how it's used. For this question, we're going to see an implementation of the linked list. It's in the examples repo. It's in week 8 linked list. Linked list node is the class that we'll see today, and the class that we'll see the base foundation of and then expand with a handful of algorithms. In that class, write a reduce function, which is going to behave like the reduce method that we've seen in the functional programming side of things. It is going to take a function that takes 2 values of the type parameter of the linked list, so whatever type the linked list is storing, it takes 2 of those, it returns one of them, and it'll ultimately return one instance of that thing. This reduce is going to combine all of the elements of the list into a single value using the reduce function, and using the reduce function to be able to combine all those elements. If there's only one element in the list, or rather the base case of your recursion, just return that one element, don't apply any function. So if I have a list 462 and I call reduce with the add function, we should get all those values summed together. That's our goal for the lecture question today. So let's where's the examples repo? It's been on the top of the course website since day 1. It's the GitHub logo. We used that in lab 1. Yeah, oof. So let's do a little background on arrays. If we recall how an array works, an array is a continuous block of memory, and to get a specific value in an array, we're going to take the element of the first address, which we're always going to have access to, and we're going to add to that whatever index we're trying to access times the size of an element of the list. So if this is ints or doubles or references, whatever the size of that element is, we're going to multiply that by the index, add it to the first address, and that's going to directly give us the memory address of the value we're looking for. So if we want the second element of an array, the index 2, we do 1 multiplication, 1 addition, and we can access that value directly. This is what we call random access. This is called random access, where you can just randomly access any element in O of 1 time. Very fast lookup for an array. But it is fixed size. Since we need 1 continuous block of memory, we can't expand the size of an array. It just can't happen, can't be done, because that next byte of memory might be used by another program, and even if it's not, we just might not have access to it. We can't rely on that next block being open. So we can't expand the size of an array. Some languages, I mean, you're used to Python and JavaScript, they'll automatically not expand the array, but to simulate expanding an array, you have to create a brand new array of a larger size, copy all of the values over to that new array, and then add the element to that new array of a larger size. Python, JavaScript, Java, if you use an array list, it'll do this resizing for you, so you don't have to think about it, but it is very inefficient when we have this resize happening, because we have to create a whole new array. So if we have an array on our heap, we have all of the values sequentially in memory. And then on the stack, any variable that stores that array is just going to store the reference to the first element of the array. So that's the only thing we have on the stack, is the value of the first element of the array, that memory address. And to find any other element, we're going to do this quick math, take the index times the size, and add to it that first value. And that's going to get us right to whatever value we're looking for. So we can very quickly find any element that we're looking for. A linked list is still sequential. It's a sequential data structure, meaning that the order matters. We have these values in a distinct order, which is not true for a data structure like a map where order doesn't matter. That's not a sequential data structure. This is sequential, except all the values are spread across memory. We no longer have this sequential data structure. We have values that can be anywhere in memory. Each value can be somewhere. We don't care where it is, but it can be anywhere, wherever the operating system, wherever the JVM decides to allocate memory for us. That's where these values are going to be. So to actually get this sequential behavior, when our values are all over memory, each value is going to contain a memory address to the next element. So each value knows what its value is and where to find the next element in the list. And that's it. That's all a linked list, a value in a linked list knows, is those two values. And with that, we have to build all the functionality that we want. How do we get all the functionality we need out of this thing? Whoa. So, for example, to navigate the whole list, we start at the first element. It knows where the next element is, so we go to that element. That element knows where the third element is. We go to that element, and then that element knows where the next one is, and we can navigate through the entire list by continuously following the memory address for the next element. So this gives us variable size that the array did not have. If we want to add an element to a list, we just say, hey, operating system, JVM, give us memory for one more value in this linked list. It gives us memory. We don't know or care where it is, but we get that address to where that new value is. We store that address, and then we can tell that new element, hey, your next address is the first element of the list that we already had. Or if we want to add to the end of a list, if we want to append to the end, we could update the last node of the list and say, you're now pointing to this new memory address, which has issues if the list is immutable that we talked about earlier, and we can talk about more of that as we go, as we get into this. But let's get the base level content out here first. So if we have a linked list, instead of an array where we had one continuous block in the heap, now we have values spread across the heap that only know where the next element is. On the stack, or any variable that stores this list, is only going to have a reference to the first element in the list, which we call the head of the list. So if I have this list, I want to create a list that has the values 5, 3, and 1. I have a node that I create with the value 5. That's going to point to the next node at some memory address. I just chose randomly 795. That's going to be the next, the address for the next node. That node has some value 3 and a memory address for the next node. That next node at memory address 416 has the value of the next value in the list. And then that next value for the last element in the node is going to be null, which we call null terminated. This isn't exactly the Scala way of doing things, is to have a null here. We're going to do this partly, at least in part, because in CSE 220 you're going to see this. Everything's going to be null terminated when you're programming in C. You're going to see nulls. You're going to see things like that. You're going to see the null terminated lists, null terminated strings, which are just character arrays in C, things like that. So if the next value is null, that means we got the end of the list. We reached the end of the list. So in our code, this is what the class is going to look like. This is what it looks like in the example repo, except it has the methods that we're going to see throughout the lecture. So the linked list node class is going to take a type parameter. We can have linked lists that store any type. And each node is going to have its value and a reference to the next node in the list. And that's it. That's all a node actually knows. And it's going to have some methods so we can do some computation on this thing. And notably, this is a mutable list. I'm using var here. So we're past the pure immutable part of the course. We're going to use var for this linked list node example, for this example that we'll see. So this is going to be a mutable list. And we'll talk about, each time it's relevant, we're going to talk about what the immutable list version of this would be, and what the implications of that would be. And specifically we're going to talk about mutable because linked lists are just one of those fundamental CS things. It's one of those things that in a lot of job interviews, they're going to ask you about the mutable version of linked lists. It's just one of those fundamental things. So I'd be doing you a disservice if I only talked about immutable lists, because it's just not what the interviewer is going to be expecting. So just a little practical note of that, why I need to talk about mutable lists, even though Scala doesn't really like mutable lists. The Scala community. Yes, you're allowed to use var for these lecture questions. The restrictions are gone at this part of the course. So linked list algorithms. So how do we do things with this list? What we talked about there, this definition, this is what a list is. This is a linked list. There's not much more to say about a linked list fundamentally. That's the structure of a linked list. It has its value. It has a reference to the next node. That's it. So the question is, how do we work with this thing? If that's all we have, that's all the structure that we have of a linked list, how do we do the things that we want to do? We want to do a lot of different things on these lists. We would like to have the functionality that we're used to. We like to call .size to find a list. We like to print out a list. We want to find values, add, remove values. I'm not going to read all of them. Fine, I will. Access elements by location. Read all of them now. So let's see how to do these, and I'm just going to go through these kind of rapid fire one by one and see examples of how to implement a lot of these algorithms. And with in mind, I'm sure you all have this in mind, keeping in mind that you have to implement reduce. So thinking of these as examples, how would you take these ideas and implement that reduce functionality given the functionality that we'll see? So let's start off easy, size. And I'm going to show the recursive examples whenever I can. The recursive examples, at least in my opinion, make more sense for linked lists. But more importantly, recursive examples are going to be a significant amount simpler when we start talking about trees than the iterative examples if you're trying to use loops. So if you get used to the recursion now, if you got used to the recursion over functional programming where we did some recursion, if you're used to that recursion before we go into trees won't be as confusing. They won't be as big of a deal. But when we do tree traversals, I'll show the recursive ways of doing tree traversals, which are pretty straightforward. But if you tried to implement them using loops, they're pretty tricky. They're pretty tricky to implement. So let's take a look at the recursive examples for this. The size, if next is null, I have the last element of a list. That's our base case. That's our trivial input-output behavior. If I have the end of a list, the next element is null, the size is 1. I just have one node. There's nothing to compute. If I'm not the last node, I'm going to ask the next node for its size recursively, and I'm going to add 1 to that for my value, my contribution to the size of this list, the node that's being called right now. So the first node, the head of the list, is going to add 1 to the size of the next node. That next node is going to add 1 to the size of that next node, and so on and so forth until we get to the base case, which will return 1 that second to last node is going to get 1 here and return 2. The third to last node is going to get 2 here and return 3. The fourth to last node, did I miss one in there? Is going to get 3, add 1, and return 4. I might have said that wrong, but I think you get the idea there. Dude, now is not the time to talk about lecture questions. Goodness. Yeah. I did dox a student. Come at me. I'll try to not pay attention to chat too much, but I'll get distracted. But after, for the Q&A, I'll be watching the chat. It was an innocent doxing. It wasn't. I didn't release private information. That's my defense. So toString, kind of the same as sum or as size. Similar to that, if this is the last element of the list, we're going to return its toString value. If I have a list of size 1, I'm just going to return its value as a string. That's it. I'm just going to return that. If I'm not the last element, so our recursive step, our base case trivial input-output behavior, a list of size 1, else I want to take the toString of the next element of the list and concatenate that with the toString of this specific element of the list. So the same way that size is going to collect all of the return values coming up the recursion is going to do the same thing. My last element is going to return its values toString. And the second to last element is going to get just that element as a string. We're going to concatenate a comma and get this values toString and return that. The third to last element, its next.toString is going to get those two elements comma separated, append its value to it and return that. The fourth to last element is going to get 3 elements comma separated, concatenate a comma and append its value, and then so on, so on and so on up the recursion. And notice with the recursive setup, appending these commas is pretty trivial. If we have a loop, we have to do some check. If you are the last element, don't put the comma after, which arguably we have the same logic here, but we would have to have that in addition to the loop. We'd have to set up the loop and have a conditional to check to make sure we don't have that comma. So one little thing that recursion actually helps us with, since we have a separate base case and recursive step, that can handle the commas for us pretty easily. So I want to get an element at a specific location. This is something that you've certainly done with your lists. We use the apply method, and apply takes an int, and we kind of treat that as an index of sorts. We can think of it as an index, but a linked list has no semblance of index. There are no indices in a linked list. So we think of it as an index if we're used to thinking about arrays, but it is definitely not an index, and this is why. When we say index, or when we say apply of some value in a linked list, we can't just do some simple math like we did with an array to find the memory address of the value we're looking for. With an array, it was just a multiplication and an addition, and we had that reference, we had that memory address immediately, O of 1 computation. With a linked list, we have to traverse this list until we find the element we're looking for. So if I do apply of 4, this is the same as saying this dot next dot next dot next dot next. So whatever node I'm looking at, give me the reference to the next node, give me the reference to the next node after that, give me the reference to the next node after that, give me the reference to the next node after that. So this is a lot of work. This is O of n work. If we say apply of 4, we're doing 4 units of computation. If we say apply of 1,000, we're doing 1,000 units of computation. So this is a very expensive operation compared to an array. Now again, 116, I've said this throughout the semester, you'll probably get away with it if you use apply throughout the course. In 250, you're going to have to be very aware of this. You're going to talk at length about the disadvantage of this, and you have to know the runtimes and all that stuff. But this is what apply has to do: is call apply. Call next that I number of times. So recursively, if I is 0, I have to call next 0 times while I'm at the element I'm looking for. Apply of 0 on the head element is just the head itself, the head element itself. So if I is 0, just return this node, whatever node this is being called on. And again, we're inside the linked list node class where all these are defined. So if I call apply of 1 on a linked list node, or apply of 0, just return that node itself. We have no traversing to do. The recursive step, we're going to call apply of I minus 1 on the next node. So go to the next node in the list, go to that, follow that reference for next, and call apply of I minus 1. So we went one step. That's what we just did here. We called next once. So now we have to call next I minus 1 times on that next node. So we can get that behavior that we want. And partly just because I want to test some more of my setup here. I tested this in 3.12 and it worked fine, so I'm not concerned. But just to make sure that we know what's going on here, let's seamlessly switch to the code. Whoa! And take a look at this class. Live, that would have been a pain in the ass getting the code up. It would have been a bit of a change, exiting full screen and everything. We're set up, man. So this linked list node class, this is what we started with. We just had value and a reference to the next node, and we're adding all these methods that we're looking at to this class. So we have the linked list node class. Here's our size method. We call this on a linked list node, and it's going to access its next, which is the next linked list node in the list, and recursively call size on that. If next is null, then we're going to just return 1. So this is where all these methods are living, is inside the linked list node class. And of course, for your homework, this class is where you'll add your reduce method. Why is this still in here? Oh, because I didn't pull. Gone. So this is where all this action is happening, is inside this linked list node class. So a linked list itself, I mean, you can set your code up to have a linked list class and have that exist, but a linked list itself doesn't really exist. A linked list is just a linked list node. When we have a linked list, when we want to think of something as a linked list, what we'll do is create a linked list node and store that in a variable and just have a reference to the first node in the list, which we call the head node. So once we have, here I create my list 531. Once I have this list, a reference to this list, this is the head of the list, and I just treat that first node in the list as the list itself. That's all a list is. When you have a list in Scala, it's just a reference to the first list, the first node in the list. It's not actually a list itself. There's no such thing as a list. There's just linked list nodes. And that's what that : class is. If you ever bother digging around through the Scala code, that : class is a linked list representation of a linked list node in Scala. So let's get back to some more methods. For add and delete, I think the visuals are more helpful than just seeing the code. So let's see some visuals for adding and removing elements specifically in a mutable list. This doesn't work in immutable lists. So adding an element, we need a reference to the node right before the element that we want to add, the location that we want to add. So if we have, say we want to add 2, we want to add the value 2 right after the value 3 in this list. So we want 2 to go right here. We can do that with a list just by updating the next references of our list. So if we want to add that value, we want 3, which currently its next value is pointing to this node with value 1, and this next is null. This is the end of the list. We want to update these references to be able to add that 2 into the list. So what we want when we're done, my cursor's on the wrong screen again. I'm going to do that quite a bit until I get used to this. We have these references, and we want to update these references to get that node, a new node with the value 2, in right here after 3. So to do that, we need a reference to this node containing 3, a reference to the node before the node that we want to add. We're going to update the pointer or the reference of the next of this node to refer to the new node that we create. And the new node that we create should have a reference to the node that was the next value. Whatever next was pointing to here needs to be what next here points to. So that's what we need to get done. We want to add this element, and we're going to do that just by updating the references. And this is where the question earlier, why not just use an array? This is the big reason why to use lists over arrays. I just added an element to the middle of a list, and it wasn't that big of a deal. I just updated 2 references. Well, this is a brand new reference, so really I just updated 1 reference, and that's it. Other than that, it was just creating my new element. In an array with sequential data, I would have to copy everything that comes after the element I'm adding. I would have to copy all of that and move it all down 1 space in the array. It's a lot of copying. If I want to add an element right before the first element in an array, if I want to make array of 0 some element, I have to push the entire array down 1 space of memory. So I have to copy O of n elements. Very expensive operation. Same with deletion from an array. So if you have this case where you constantly need to add and remove elements from a data structure, a list is going to be more efficient than an array, especially, as we'll see, if you're adding and removing from the head of the list constantly, and only the head of the list. A list is way more efficient than an array. I'll talk about it a bit in this class, but again, that's a lot of 250 territory. They're going to go, Dr. Hughes will go way in depth with that. So here's the code for that. If I have a reference to the element that I want before the element that I want to add, I'm going to call insert from that element. So I'm inside the node where I want to insert. I'm going to call insert of that element on that node. So this would be the node 3. In this example, I would be on this node. This would be the keyword this would refer to this node in this case. So this.next is going to equal some new node containing the element that I want to add to in our example. And then this.next, whatever this.next was, I want this new node to refer to that element. And then this element is now going to refer to the new node. And since the right side of the equal will be evaluated before the left side, this.next is going to refer to that old value. That's going to refer to this node. And then after this is all evaluated, this new node is going to be assigned to this.next. So this.next after this line evaluates is going to refer to that new node that we just created. Excuse me. Imagine you have a pile of bananas. Deleting a node, similar to adding, we need a reference to the node before the node that we want to remove. This is the node where we have to start updating these pointers. We don't need a reference, or we can't only have a reference to the node that we want to delete, because the node before the node we want to delete, that's the reference that we need to update. We need to update this reference. So just having a reference to the node we want to delete isn't going to get us what we want. We just can't get there. But we have a reference to the node before the node we want to delete. We're going to take its next value and assign it to next.next. And just completely cut this node out of the list. That node is no longer part of the list now. This node still refers to this node storing the value 1. But who cares? Because we don't have access to this anymore. It's just completely cut out of the list. If you're traversing this list, you're going to start here, go here, go here, and then find the end of the list. You're never going to find this node 2. It just doesn't exist in this list anymore. Somebody else might have a reference to this list and still have the list 2.1 null, and we're not affecting them, but this is effectively cut out of the list that we just worked on, that we just updated. And the code is pretty simple for that. This.next equals this.next.next. So whatever my next node is referring to, that's now what I refer to, and this.next, whatever that was, that node is gone. Is there a lecture question for March 13th? If that was the Friday before spring break, then no. There's only 5 lecture questions in functional programming. Given all the coronavirus stuff, it made more sense to just scrap a question, not pile on your workload in the middle of everything. All right. Finding a value. So let's look at one. Oh, excuse me. Let's look at some a little bit more complex. Still not getting too crazy. I mean, I guess there's nothing too crazy that we look at with linked lists. But let's look at another algorithm. Finding a value. Oops. We want to find a value by its value. So we want to find a node that matches a value that we're looking for. So I had some list. Maybe it's a list of ints. And I want to say, find me the value 5 in this list of ints. And specifically, our method is going to return a reference to a node containing the first node that matches the value we're looking for. So if 5 is duplicated in this list, we're going to return the first one that we find. And if 5 is not in the list at all, we want to return null. To indicate that we didn't find the element at all. So to do this, we're going to use recursion again. If we call find on a node that contains the element that we're looking for, we're done. That's our trivial base case. If this dot value equals the value we're looking for, donezo, return a reference to this node that contained that value. We want a reference to the node containing the value that we're looking for. So return that reference to the node. Else, if we are at the end of the list, return null. So remember, this is an else if. So if we're checking this value, if we're checking this conditional must have already been false. So this can be read if this dot value does not equal to find and we're at the end of the list. So if this node does not contain what we're looking for and we're at the end of the list, return null. That means we made it through the entire list, didn't find what we're looking for, just return null. Else, make the recursive call. Go to the next node, call find on toFind, and maybe the next node has better luck than we did because that node did not contain the value we're looking for, and it's not the end of the list. So keep going down the list and keep looking for that value. I have to resist the urge to stop and ask for questions because the questions just come asynchronously now. And the questions are about bananas. That's not helpful. Okay, so I just want to show at least one example of iteration. I know iteration is kind of the natural way that you want to think about these if you're still resisting recursion, but I at least want to show one example. In my opinion, the recursive method is cleaner in here, but you can make your own judgments. The iterative version would be to initialize the node that we're looking at to be the first node, whatever node we're currently looking at. This is initially called on the head of the list, so you can think of this as node equaling the head of the list. And as long as the node we're looking at isn't null, check if it's the value we're looking for. If it is, return that node. If it's not, advance to the next node in the list and try it again. Does this node have what we're looking for? If it does, return it. If not, advance to the next one. And keep going through the list until we either found the node we're looking for or we've reached the end of the list without finding it. If we reach the end of the list without finding it, return null. So the same thing, I would argue that this is cleaner. The recursive method is cleaner and easier to read, but whatever works for you is what's the best approach. But this would be the difference between the iterative and recursive methods. For linked lists, it is debatable. You could argue that this is a better way to do the iterative version. Again, for trees, I don't think you're winning that argument. All right. Let's get to our first. Method that takes in a function. Let's take our first method that takes a function for each. So to get you used to the method that we'll use in the lecture question, which is going to be to take in a function in your method and apply that to your list. So let's see the simplest way of doing this for each. Just take a function and call that function on each element of the linked list. So for example, if we wanted to call head of a list dot for each *,
print line just to print out a whole list with one value per line. Let's see how to do that. So we're going to we call this for each on a node. We're going to call the function on the value of that node to get that node's value, the function call on that node's value, get that work done, and then go to that next element. If this is not the end of the list, call for each on the next node. For each on the next node is going to call the function on its value, and then if we're not at the end of the list, just keep going down the list. Keep going down the list until we reach the end while calling the function at each step of the way. Arguably, this one would be a little cleaner with a loop. This effectively reads like a loop. Well, this dot next not equals null, f of this dot value. And then, we'd have to store the node. Yeah, it's a little not as clean as I'd want it, but. And finally, map. So map, recall from functional programming, map is where we have a data structure. We want to take in a function and return a new data structure with that function applied to each element. So we want to call map. We give it some function. In this case, I'm going to square each integer. I have a list of ints, and when I call map with this function, I'm going to get a new list with this function applied to every single element of the list and return that brand new list, and I can print it out and see that I get what I want out of that. So this is the functionality we want. This is the functionality that we saw in functional programming, and we would just call this built-in map function. This is the built-in Scala list, and we just call map on it. So that's how we did it from the user side. Now as a developer implementing a list, how do we build that? Well, I'm glad you asked. Apply that function to each element of the list. So this, we want to call that function on each element of the list, similar to for each, but we have a bit more work to do because we want to eventually return a reference to the head node of this list. So if we call map on the head of a list, we want to make sure that returns a reference to the new linked list node that we created that's the new head of the list. So instead of just calling that function and relying on the side effects like we did with for each, because with for each we have a function that returns unit, now we have a return value and we want to do something with that return value. So we're going to store this new value that we've created. We've applied this function to the value of a particular linked list node, and we want to store that in a value, in some variable. I mean, we could do this outside of this. I just want to break this into separate steps. Store this in a variable, and if we're at the end of the list, we have our base case. If we're at the end of the list, we want to return a new linked list node with that value that refers to null, and we're going to return that back up the recursion. If this is not the end of the list, we have our recursive case, and we want to return a new linked list node with that value, same thing, with that new value. Oh, that's why I want to start in a variable because I'd have to have f of this dot value twice, which wouldn't be the worst thing. We want to create a new node with that value, except instead of pointing to null, we're not at the end of the list. So we're going to have this node refer to the recursive call of map on the next node of the list. So there's quite a bit going on in this little part right here. This is where all the recursive power is happening, is we're calling map on the next node of the list with that same function. This is going to return a node with that function applied containing that points to all of the remaining elements of the list with that map function applied to it. If we refer to that node and return that value, we have that whole tail of the list with also this node added to it. So if we think of our base case is going to apply the function to its value if it's the last element of the list and return a new node with that new value pointing to null. That's what this will resolve to in the second to last node of the list. So the second to last node of the list, this is going to resolve to a node with the new value for the last element of the list referring to null. We're going to add that new value, point to the last value, and then return that to the third to last element of the list. The third to last element gets a reference to the second to last element with the function applied, which has a reference to the last element with the function applied, which has a reference to null, it's going to have refer to that as its next, have its new value with the function applied, and keep returning up the recursion until eventually we get back to the head of the list, which is going to return the head to the new list that was created. So we just created a brand new node for every single node in the list, created a whole brand new list with all the linking the way we want it to be, and then return the head of that brand new list that we had, that we created. We didn't see this, did we? I think I briefly showed it, and I'm only briefly showing it again here. I haven't required it for a lecture question yet. But we can change the type through map as well. When you call, we did this from the user side. We called map with changing types, but we haven't seen it on the developer side, writing methods with 2 type parameters. But if we want our map method to be able to change the type of a list, we can have the map method itself take a type parameter, which can be different than the type parameter of the list itself. So this A type parameter, we're getting this from the list itself. The list has this type parameter A, and this method takes a second type parameter B to be able to map to a different type. So now our method is going to take a value of the type of the list and return a value of the type of the new list, and the nodes that we return are going to be of type B, the type that we just changed to. So for example, if we want to take a list of ints and divide each value by 2, and we don't want the truncation, we don't want integer division, we want to keep the decimal values, we can have a map function divide by 2, take in ints and return doubles, and convert our list of ints to a list of doubles using this map function, using this map method with a function that takes ints and returns doubles. Or if we want like the lengths of the string like we saw before, the lengths of the string, you could do the same thing. Have a function, takes a string, returns an int, calls that string.length, returns that value, and get a new list with all the lengths of those strings. Which brings us back to our lecture question.